To start off Chapter 2, we're going to be talking about relations and functions. How do we graph relations and how do we identify functions? First off, what is a relation? It is a set of input and output values, and then come in lots of different ways. Let's look at one example here of different ways that we could represent this relation. The data shows the various heights of a skydiver at different times during the fall. Represent the data in 4 ways. First way is as an ordered pair. This is typically found as an x value, then a y value, inside a set of parentheses. If we look at the data, it seems to already be in ordered pairs, but we're going to want to take off the units. So the first one would be 0, 10,000. The second would be 4, 9,744. Then 8, 8,976. And then the last one is 12, 7,696. The second way is with a mapping diagram. Here you're going to have a line of your inputs as well as a line of the outputs. And you're going to make sure that the inputs and outputs go in increasing order. That's important to remember. So for the input, we're going to start with 0, 4, 8, and 12. Then for the output, we have 7,696, 8,976, 9,744, and 10,000. Then, in order to make it mapping, we need to have arrows to show which input corresponds to which output. So 0 goes to 10,000, 4 goes to the third to last, 8 goes to the second one, and 12 goes up to our first one. Next, we have a table of values, which is really similar to the mapping diagram, but now we include units and there is no arrows. So now for our input, we have the time, and that time is in seconds. And for the output, we have the height, or the feet. And then we can put the corresponding data. So we have, at 0 seconds, 10,000 feet, 4 seconds, 9,744, 8 seconds, 8,976, and 12 seconds, 7,696. So with the table of values, you do not need to worry about putting them in increasing order. Make sure that the data corresponds like it does in the ordered pairs. Then we can have a graph. And a graph then gives us a visual way of representing the data from that table. So on the x-axis, we're going to have our input, which is our time, in seconds, and the y-axis we are going to have the height in feet, or the output. Then we need to come up with a scale. We can go up by 4s for time, so we'll have 4, 8, and 12, and then let's go up by 2,000s for the height. So 2, 4, 6, 8, 10, and then we'll label that 2,000, 4,000, 6,000, 8,000, and 10,000. Now we can plot each point. We'll have 0, 10,000, 4, then somewhere roughly about 9,700. 8 seconds, we're at basically 9,000. And then at 12 seconds, we're at about 7,500. So maybe right about there. With our graphs, we could change the scale to make this a little bit more accurate, but this is sufficient to represent data. Now let's talk about finding the domain and the range of a relation. The domain are your input values, also known as the x values, whereas the range is the output values, or the y values. So when we're given a set of ordered pairs, remember that these always come in the format of x, y. So the domain, in this case, is going to be all of the first numbers in the ordered pairs. But when it comes to writing the domain, make sure again you put it in increasing order. So our smallest value was -3, then we had 0, 2, 9, and 23. Then for our range, that's the second number in the ordered pairs. But we also want to put these in increasing value. We had smallest value was -99, then -18, then we had 0, 7, and +14 for the last one. Pause the video and use the data from example 1 to identify the domain and the range. This is what you should have got. Also notice how both the domain and the range are always going in increasing order. If you did not put them in increasing order, go ahead and switch that up. What a relation is, we can introduce the idea of a function. Now, a function is a relation where no number in the domain is repeated. Meaning, if we have some value for x or some input value, we cannot have it a second time. We cannot have it correspond to two different numbers in the output. Mapping diagrams can be a really great way to see this. If we track the arrows, we can see the input goes to one output, 20 goes to 45, 30 to 25, and 40 to 35. We have not repeated any of those input values, so this would be a function. Another way to look at them would be through ordered pairs. Now remember, with ordered pairs, the x value always comes first. So here we're looking simply at the domain, 4, 8, 1, 6, and 4. Any of those domain values repeat, and they do. So this one is not a function, and that's because the 4 repeats. But again, notice how we're only looking at the domain, we are not looking at the range. Go ahead and give C and D a try. Going to be a function because the value of 2 corresponds to both 20 and to 40. That means we have repeated that value in the input. On D, though, it will be a function because we have all different values for x, and there are no repeated values in the domain. One other way to identify a function is through what we call the vertical line test. And that says if a vertical line passes through more than one point on a relation, then it is not going to be a function. Now remember, vertical lines, these are the ones that go straight up and down. So let's go ahead with this first one, draw a vertical line. This one touches at 2 points, so this one will not be a function. Down, if we draw a vertical line, we could draw them even through several different areas of the graph. Doesn't matter where we go, it's only ever crossing at 1 point. So this one would be a function. Okay, let's move back to the middle here. Again, draw some vertical lines, and at each point it's still only crossing once. So this one is a function. Go ahead, pause the video, and give those last 3 a try on your own. The 2 on the bottom would both be functions because they pass the vertical line test, but this one left here up on the top is not going to be a function because, again, it's crossing through the graph at 2 different places with that vertical line. Now we're going to take a look at function notation. In the past, we've seen a lot of equations like y equals 3x plus 2. But if we know that an equation is a function, we have a new way that we can write it. And that is f of x equals 3x plus 2. So instead of writing y equals 3x plus 2, we're going to replace the y with f of x. They mean the same thing, except we know that because it has f of x, we're dealing with a function. Then when we have f parentheses x equals 3x plus 2, how that really reads is f of x equals 3x plus 2. In the first example, we have f of x equals negative 2x plus 5. That x just tells us what we're plugging into the function. Since we know that x is equal to 1/4, we're going to take this 1/4 and we're going to plug it in to our function notation, and we also plug it in for x in the equation. So we're going to have f of 1/4 is equal to negative 2 times 1/4 plus 5. Now we can ignore the left-hand side because all it is telling us what number we plugged in. There's no operation, there's no calculation to do on the left. On the right-hand side, though, we have order of operations. We have an expression that we need to evaluate. So negative 2 times 1/4 is negative 1/2 plus 5, which equals 4.5. Now, sometimes we might see instead of using f as our variable, we might use a different variable. So in this case, we have h of x equals negative x cubed minus 7x. We're going to find the output for x when it's -7 and when it's 2. So let's start off with our -7. We're going to take that -7, and that's what goes into our function notation. So we're going to have h of -7. Then that's just telling us in our equation, anywhere we had an x, it gets replaced with a -7. So we're going to have a negative times -7 cubed minus 7 times -7. Now, all we need to do is evaluate. Remember, as long as we're putting our parentheses in the correct place, we could plug this right into our calculator. Or if we're doing order of operations by hand, we're going to start off with doing that -7 cubed, which is -343, still being multiplied by that negative outside. Then -7 times -7 is +49. So we're going to have 343 plus 49, and that gives us 392. Pause the video and give it a try with plugging in 2 instead of -7. The notation should be h of 2. Then you're just going to plug in a 2 for x in each spot in the equation. Order of operations, and you should end up with -22. Now that we know how to evaluate functions, let's go over how to write a function in function notation. So let's say that the tickets to a concert cost $35 plus a handling fee of $2.50. The total cost is a function of the number of tickets bought. What function rule models the cost of the tickets? Let's start with that first question before we evaluate. So first, when we're talking about a function rule, it just means we need to write an equation in function notation. That means we're going to have two different variables. So we know that the cost is a function of the number of tickets bought. Let's represent cost with a C and tickets with a T. It tells us that cost is the function, so it's going to take place of the F in our function notation. So we're going to now have C of T, since T is what's changing, the number of tickets that people buy. And the number of tickets they buy then determines the cost. That's why T goes on the inside. Well, this has to be equal to the rest of our equation. How are we going to find the cost? Well, we know that they cost $35 plus, which tells us we're going to be using addition, a handling fee of $2.50. So we know we're going to have 35 plus $2.50. But now we need to see, where does this variable of T go? Since T represents our tickets, we're going to have to multiply it by the 35, since that's the cost of each ticket. Then the $2.50, it's added on no matter how many tickets you buy, so it just stays off to the side by itself. Now that we have our function rule, we can go ahead and we can evaluate the function for 4 tickets. So we'd have C of 4, or the cost of 4 tickets, is equal to 35 times 4 plus $2.50. And this comes out to be $142.50 to buy 4 tickets.